Hello. Yeah. Firstly, welcome everyone, both first-comers as well as regulars to ICTS. And we are very glad that we are having this exciting public lecture today to celebrate the momentous discovery of LIGO. And in fact, ever since the LIGO announcement, all of us here at ICTS many of us here have been on a bit of a high because we are very, of course, the discovery was amazing, but we are particularly proud that a team here of very young people has made significant contributions to the understanding and the analysis of the signal that was detected. So in fact, just a day after the announcement, we had organized a public event which had conveyed the excitement and of the discovery to a general scientific audience. And these last few days, there has been a meeting, a very stimulating meeting here by a number of the experts from India and abroad on this discovery and the future that it heralds, especially in the light of including the fact, among other things, the fact that LIGO-India is slated to be built. So the public lecture today is part of this ongoing meeting, and in fact we are very glad that an eminent scientist like Professor Stanley Whitcomb, who has been at the heart of the LIGO science collaboration, has agreed to give this lecture. Public lectures like these are sort of one prong of ICTS's mission, which is outreach, communicating the excitement of scientific discovery more largely. And we, in fact, these lectures are archived and viewed by many more people than the ones in Bangalore or who are here at this moment of space and time. It's something that has a wider ripple. The other prongs of ICTS's mandate are, of course, scientific research at the very highest levels, and that's exemplified by our LIGO team here. And finally, to organize scientific programs and meetings like the present one that I mentioned, which would bring together the best in India and abroad for exchanging knowledge and brainstorming and coming up with new ideas. And I'm very happy to hear that this brainstorming here has been a very stimulating one. I would also like to sort of welcome to our campus and in our midst Sri Narayana Murthy, who is to many, all of you, I don't need to introduce him, the visionary leader and founder of Infosys. And Sri Murthy has been championing for excellence at every stage. And I think we are very fortunate that he has reposed his confidence in us, and the Infosys Foundation has supported many of the activities of ICTS, including that of the research works of the ICTS LIGO members. So I would therefore like to invite Sri Narayana Murthy to come onto the stage and present a small memento to our speaker, Professor Stan Whitcomb.
Hello. On behalf of all of you, I'm delighted to welcome Stan Whitcomb to ICTS and to deliver this evening's public lecture. Stan is the chief scientist at LIGO Caltech. He did his PhD in 1980 at the University of Chicago. And in LIGO, he has really had a variety of roles. He has been the chief scientist, the deputy director, the detector group leader, the R&D group leader, and so on. And more recently, he was also a member of the detection committee, which finally allowed us to sign off the discovery. Stan, as you will realize when you talk to him, has also worked in the industry for many years. He has been very instrumental for the last 35 years, as you heard in the panel discussion. He has been involved in the attempt to discover gravity waves, and therefore, what you can learn from him just by chatting is something one should never miss. So do catch him and try to pick on his brains if you have anything to ask, because as I've realized, there's a lot you can learn from him. Stan has awards. He has been awarded. He's a fellow of the Optical Society of America in 2012 and the APS Fellow in 2002. He has been the executive secretary of GWIC, the Gravitational-wave International Committee, from 2007. And GWIC really helped us and held our hands, and especially Stan himself, when from 2009 and 2011 onwards, we really tried to put our foot forward and try to get towards a detector in India. He has also been the chair of the topical group on gravitation in the American Physical Society. And as I mentioned, he has been the coordinator from the LIGO lab on LIGO-India from almost the beginning. I had the pleasure to meet Stan in Australia when we were looking at LIGO Australia. And from that day onwards, I think he has been a mentor to me. As you can imagine, it's the most unlikely person to look at something like LIGO-India. And the only reason I managed to survive these few years is basically because of the many, many tutorials I had from Stan on the experimental aspects of gravitational radiation. So without much ado, let me give you Stan, Whispers from Space.
Thank you very much, Bala. It's a great pleasure to be here, and in particular in this auditorium named after the famous scientist Chandrasekhar. I met Chandrasekhar when I was at the University of Chicago. Always lived in a little bit of fear of him because of his great intellect and his very high standards, but I came to grow to feel very close to him in the end as well. So it's a very great pleasure to be here for that reason. Our story begins 1.3 billion years ago in a distant galaxy. And if you had been there in that galaxy, this is what we would have seen. These are two black holes orbiting each other. We're looking at the stars behind them as they're imaged around the black hole through gravitational lensing. Those black holes are radiating gravitational waves. That's causing the system to lose energy, and they move slowly closer and closer together until finally they touch, merge, and form a single object with a brief ring down, and then it becomes quiescent and stops. Was that too difficult to see? Should I play it again? Okay. So we see the stars from behind. They're imaged. You see ones, they'll disappear and then reappear on the other side of one of the black holes. This is a real simulation. It's not an artist's conception. It's a real simulation of what would happen to the light from the stars in the background as these two objects rotate together, merge, and then vibrate, and then settle down into a final quiet configuration. There's something else that happened, however. During that period of time, those two black holes radiated gravitational waves. Those gravitational waves carry the information about what was happening to those two black holes. Those waves spread out through the galaxy, traveling this 1.3 billion years from then to now, until they passed through the Earth. When they passed through the Earth, they caused the Earth to change shape slightly, to oscillate, as space itself is being stretched and squeezed by the gravitational wave. And again, that stretching and squeezing carries with it the imprint of the motion of those black holes. We detected that at this LIGO facility in Hanford, Washington. I'll come back and tell you a little bit more about the detectors later on. So on September 14th last year, after traveling that 1.3 billion years at the two LIGO sites, we saw the following. So normally these two LIGO detectors are sitting there waiting for gravitational wave output at Hanford. This is the detector output at Livingston. It looks just kind of a little bit of random noise. At that particular time, on September 14th, we saw this extra little bit of wiggle. We saw the same extra little bit of wiggle at Livingston. And by taking those two data sets, comparing them, we were able to conclude that it was these two black holes a billion light years away. And as a result, when we announced that result, it was front page news pretty much around the world. This is a compilation of newspapers from the next day after we made our announcement, from all over the world, from Europe, from Asia, from South America, all over the world. This was front page news. And what I want to do today is tell you, why was this such a big story? What made it so important? I want to tell you a little bit about the background and the history of how we got to this place, tell you a little bit about the remarkable instruments that made this discovery, tell you a little bit about what it means. And I will actually walk you through those last figures that I showed you and point out what are the essential features and why do we know that these were two black holes. And then I want to talk to you a little bit about what comes next and the role that India will be playing on that. So our story actually goes back to 1686. In that year, Newton published his volume of physics results called Principia. And included in that was his theory of gravity. He said, the story is that he was sitting under an apple tree and watched an apple fall towards the earth and realized that there were equal and opposite forces between the apple and the earth. And so his theory of gravity was that every pair of masses would pull on each other, creating equal and opposite forces. Apple is pulled towards the earth is pulled towards the sun's pulled back towards the earth. Saturn tugs on the apple, although Saturn's too small and too far away to really have the apple drop. Every pair of objects pull against each other. He embodied that in a simple formula that I'm sure everybody has seen, that the force between the objects is the product of their masses divided by their distance squared. And it was an extremely successful theory. It solved some of the known problems in astronomy and in terrestrial physics. It explained the eccentric orbits of comets and why the planets move around the sun. It explained tides and their variation, the perturbations of the motion of the moon by the gravity of the sun. All of that was pulled together by Newton's theory of gravity in that famous equation. And it unified all of the astronomical work that had gone on previously. But there was a problem. By the end of the 19th century, around the turn of the 1900s, there was one mystery, one unexplained fact, and two mysteries, in fact. The unexplained fact was that astronomers had been observing the motion of Mercury around the sun, and its perihelion, the place where it has its closest approach to the sun, seemed to move forward in the orbit by 43 arc seconds per century. That doesn't sound like a lot, but if you're an astronomer and you've been observing this and you think you've actually understood all of the other factors, you've got a problem here, because this was beyond the measurement error and it was and there was no way to explain this. In addition, people said, well, what is this mysterious force that in Newton's theory? They didn't really understand it. And finally, there was this problem. People were starting to see the theory of special relativity, which had a limit to how fast information could be transferred from one place to another. That was the speed of light. And so Newton's theory doesn't take that into account. Any body is supposed to know exactly where all the other bodies in the universe are so that it can calculate all the forces on it. And how can it know the positions of those other bodies if they're farther away than light could travel? So there was a problem. And it was solved by this guy, Albert Einstein. He put forth his theory of general relativity. It was a radical idea, and it completely overthrew the notions that we had of space and time. So up to this time, time had been absolute. Everybody's time in the entire universe was the same. You could look at your clock, I'd look at my clock. If you were in a different galaxy, you'd look at your clock, and everybody should see the same time. Einstein said no. He said, we don't really have 3 dimensions of space and time. We have 4 dimensions of something called space-time. And our perceptions of space and of time are relative. They depend upon our frame of reference. In particular, if we're moving or going faster or slower, it overturns that. Moreover, gravity, according to this theory, is not a force, but it's a property of space-time. Okay? And the idea is that concentrations of mass distort space itself, distort space-time, and that objects follow always the shortest path through this distorted space-time. So if I have two points going around the sun, and I imagine this is just we like to use this picture of an elastic membrane, and if we put a mass on it, it will stretch such that you can, it will distort where that mass is. If you have 2 points there, the shortest path no longer is that, because that membrane has been pulled down in this region. The shortest path from A to B is now that. So if you shoot a rocket from A to B, that's the path that it will follow. And notice that it looks as if this body here has pulled the path of that object going from A to B. And so suddenly we see now gravity is a distortion of space. The Earth goes around the sun not because the sun is pulling towards it, but because it's created a dimple kind of in space-time, and the Earth goes round and around in that distorted space-time. This explained, it turns out, the precession of the orbit of Mercury, gave a very accurate prediction for this. Well, not really a prediction, a post-diction. But it predicted the bending of starlight. And when a few years later, Eddington made an expedition where he actually measured the bending of starlight during a solar eclipse, as the light passed near the sun, the position of a star during an eclipse appeared to be slightly altered compared to where it would have been without the sun in that position. And that confirmed this. That was a huge confirmation for Einstein's theory of relativity. Now, this membrane picture, this idea of a space, also gives you another idea. If you were to take and dimple, just pop your finger against that membrane, what would you do? You'd create waves that propagate out from the place where you're tickling that membrane. And in fact, Einstein's theory of general relativity makes that kind of a prediction. It predicts that there are these things called gravitational waves. They're ripples in space-time, ripples in space itself that travel at the speed of light. And Einstein recognized this almost as soon as he published his theory of general relativity. A year later, he published his first paper predicting these gravitational waves. So, Einstein also calculated a few years later what would it take to make gravitational waves, and he realized that although in principle almost all moving objects produce gravitational waves, to get strong gravitational waves you have to have very, very large masses and very, very large motions, very fast motions, very large accelerations. And as a result, all measurable gravitational waves that anyone can think of, those sources are going to be astronomical. Okay? They will come from astronomy, not from anything that we can do here on Earth. For 50 years, more than 50 years, nobody really tried to detect gravitational waves. They knew that they would be very, very difficult. And then in the 70s, in 1974, two astronomers, Joseph Taylor and Richard Hulse, detected a system that would show gravitational waves, the existence of them, prove them. It was a system called the binary pulsar. It's two neutron stars that orbit each other. So each of these objects is a neutron star. It's a star that has the same mass as our sun, but it's spent all of its nuclear fuel. It's collapsed to the density of an atomic nucleus, and it's only 15 kilometers in diameter and still has all of the mass of the sun. These two stars, these two neutron stars, orbit each other in an orbit that has a period of about 8 hours. Okay? And the important thing is that one of those neutron stars is a radio pulsar. It's a neutron star that rotates, and every time it rotates, it sends a beam of light like a lighthouse. And so we see pulses from this object 17 times a second coming around in a steady pattern. And this is a very, very stable rotating system, very, very good clock, if you will. And as a result, by measuring the time of arrival of those pulses, we can trace out the motion of those neutron stars around each other. As they move in and out, the periods of the arrival of the pulses will get longer and then shorter again. And we can do that with extraordinary accuracy. These two neutron stars are separated by about 1 million kilometers in orbit around each other, and the prediction from general relativity is that they will spiral together, closer together, by about 3 millimeters per orbit. That the orbital separation will decrease by 3 millimeters per orbit because of the loss of energy of the gravitational waves. And over the subsequent years, Joseph Taylor and his collaborators measured the arrival of those pulses, and they actually saw that orbit getting shorter and shorter as the orbital period getting shorter and shorter as the two objects move closer and closer together. And the measurements that they made match exactly the prediction of general relativity. It took them several decades before it was completely unambiguous. But in the 90s, I guess it was 94, I believe, they won the Nobel Prize. Hulse and Taylor were awarded the Nobel Prize for this discovery. This is the first proof of the existence of gravitational waves, and it gave enormous push to the effort to detect gravitational waves. So let me go back now and tell you, what does a gravitational wave look like? If you imagine that we've got a circle of masses out in space, completely free from all other disturbances except for the gravitational wave. If you have a gravitational wave that's going into the plane of the screen there, so it's going straight in, what it does is it squeezes space in one dimension and stretches it in the other, and then half a cycle later stretches the first dimension and squeezes the second. And it will continue doing that as long as the gravitational wave is incident on it. And the amount of change of the separation is proportional to the initial separation. So the delta L that you would see from the separation of, say, these two particles is proportional to their initial separation. If they were half as far apart, they would be moving half as much. So in order to detect a gravitational wave, people came up with this idea of using a Michelson interferometer. So a Michelson interferometer is a simple interferometer. You take a laser beam, split it on a beam splitter, send the light down the two arms, half of it's transmitted, half of it's reflected. It comes back from those mirrors, recombines on the beam splitter, and you sense it with a photodetector out here. And this is a very, very sensitive way to measure the relative lengths here. And you can see, if you imagine that your beam splitter's sort of fixed in space, then the gravitational wave stretching space itself and shrinking it will actually cause those two arms to change length. Okay? Now, I've greatly exaggerated this effect. For a strong gravitational wave, a very strong one, that strain, delta L upon L, would be about 10 to the minus 21. And for LIGO, with 4 kilometer long arms, that means the delta L would be of the order of 4 times 10 to the minus 18 meters. Okay? Now, I'll come back to how big that is, but that's really, really, really tiny. So let me show you a little bit about how this basic interferometer works. Nope, that was not that button. So as I said, the Michelson interferometer, you take the light, it splits, goes back, and as you change the length of the interferometer, you change the amount of light that comes out to this photodetector. Remember, light is a wave. You split the wave, it goes down to the end, comes back, and depending upon how the waves from the two arms combine at this beam splitter, you can either get them to cancel the way they're doing now, so they're out of phase, and when you add them up, they cancel, or if the length of one arm changes, they will line up and interfere constructively, and you'll get a lot more light out here. And so this is the technique that we use. This is a measurement that's been around for about a century. It's a very sensitive way to measure small changes in length. But we've really had to stretch here because of we're needing something that's even more sensitive than the typical interferometer. Let me ask the question, how small is 10 to the minus 18 meters? So you know a meter is about that length, okay? A human hair is about 10,000 times finer, so it's about 0.1 millimeters. The wavelength of the light that we use is 10 to the minus 6 meters, so it's 100 times smaller than the diameter of a hair, human hair. The atomic diameter is another 10,000 times smaller than the wavelength of light at 10 to the minus 10 meters. The nucleus of the atom is another 100,000 times smaller than the diameter of the atom at 10 to the minus 15 meters. And we want to measure something that's 1,000 times smaller than that. 10 to the minus 18. It's 1/1000th the diameter of an atomic nucleus. And that's the challenge for us. So the detectors we have are called LIGO, Laser Interferometer Gravitational Wave Observatory. We actually have 2 sites. I mentioned before, one in Hanford, Washington, one in Livingston, Louisiana. They're placed about as far apart as you could do in the United States because we wanted them to be well separated so that local disturbances wouldn't cause effects on the 2 detectors. That was part of the way we know that we're seeing a gravitational wave and not some other local disturbance. We also use that large separation to help us determine where the sources of the gravitational waves are on the sky. So this is our site in Hanford. You can see this is a photograph. Our detector, the corner here where our beam splitter is, the end mirrors are out here, and the light travels through long vacuum tubes there. The infrastructure that we have, these long vacuum tubes, they're 1.2 meters in diameter. The light has to travel in an excellent vacuum. These are ultra-high vacuum tubes, so 10 to the minus 9 torr for those of you who know anything about vacuums. It's very, very good. It's large diameter, even though the laser beam is quite a bit smaller, because we don't want to have any scattering of light from the walls of the beam tubes, And the tube has got to be straight to a fraction of a centimeter because we've got to get the laser beam down it. The curvature of the Earth over that 4 kilometers is actually a couple of meters. So we want to be sure that the tube is absolutely straight, not following the curve of the Earth, because otherwise the light won't get through it. The mirrors, the optical mirrors that we have, also have to be in vacuum. So our beam splitter has to be in vacuum, so do the end mirrors, and so do a number of the other components for this. And we have large chambers in which those mirrors are suspended. These chambers are about 15 feet tall, about 5 meters tall. And they have large doors, so you can take the doors off. Actually, when you're installing the detector, you climb into the vacuum chamber and work inside there under clean room conditions. So we want to use this interferometry technique to measure 10 to the minus 18 meters. So as I said, the laser wavelength is 10 to the minus 6 meters. We need to measure something 10 to the minus 12 times smaller than the laser wavelength. There's another problem, that the ground is continually moving. You think of the ground as stable, but it's continually in motion at a level of about 10 to the minus 8 meters. So about 10 to the 10 times larger than the motion we're wanting to measure. So we've got to protect that mirror from the ground motion and keep it from moving. And finally, the mirrors themselves have internal motions. They're at thermal equilibrium. They're at room temperature. That means they have kT worth of energy in every vibrational mode of the mirror. So the mirrors are going like this, and the pendulums, they're suspended on wires. The pendulums are going like this. All of those things are going on. The thermal vibrations are of order 10 to the 12 meters, so about 10 to the 6 times larger than what we want to measure. So we've got to have tricks to use to get around those motions. So let me show you a little bit about the hardware. This is the laser we use. It's a very, very stable laser. It puts out 200 watts of 1 micron light. That's the most stable laser in the world. And that's a very high power laser, 200 watts. And the reason is we need to use all of those photons in order to be able to distinguish motions that are much smaller than the wavelength. So this is a key piece of our operation. This was contributed to us by the Laser Centrum in Hanover, part of the GEO project, our collaborators from Europe that have contributed to the LIGO interferometers. This is one of the LIGO mirrors. This mirror is fantastic. It's 35 centimeters in diameter. Over that entire surface, it's polished to 1 nanometer, 10 to the minus 9 meters accuracy, and then it's given a multi-layer dielectric coating that's uniform to plus or minus 1 atom in thickness. This object is ultra-high purity fused silica. The reflectivity of the surface here is 99.999%. So it has about 1 part per million, a little less than 1 part per million of absorption of the light that falls on it, a little bit more than that of scatter. It's extremely good mirror. It's got very high internal mechanical Q, and that helps reduce the thermal noise by pushing it out of the band of frequencies that are of interest to us. We take that mirror, which by the way costs anywhere from, depending upon the exact configuration of this mirror, anywhere from about $250,000 to $500,000. And what do? We suspend it on very, very thin glass fibers. So this mirror down here is suspended on 4 fused silica glass fibers, and those fibers are stretched to approximately half their breaking strength. So it's a real nice, it's nerve-wracking to watch people work around these things, I will tell you. This suspension system is a 4-stage system, and that's part of part of our isolation system. So we've got the mirror here is suspended from another piece of fused silica, which itself is suspended from another piece of metal up here, which itself is suspended from another piece of metal. So it's 4 stages of pendulum suspension, and that's to help reduce the amount of ground motion that's transmitted to the mirror. When this point up here shakes, it's attenuated by the pendulum, just like if you take a pendulum bob and shake it like this, the bob of the pendulum doesn't move very rapidly unless you hit right at the resonant frequency. And so each layer here gives us some isolation. In addition, we hang it from a vibration-isolated platform. This is a very complicated device. It's got a set of accelerometers and geophones that measure the motion of this platform and compensate for it by actively pushing and pulling to hold it stable. So all of this technology goes into making this very, very sensitive laser interferometer. So what do we learn from this record that I showed you before of h of t, this measurement that we made? So what I told you that this was 2 black holes orbiting each other. And so I'm going to say, well, what does it look like? What are the gravitational waves from that system look like? As these 2 black holes orbit, you get a sinusoidal gravitational wave that's gradually increasing both in amplitude and in frequency. As they spiral together, they're going faster and faster, so you get a higher frequency. Eventually, they touch, merge, and then there's this final kind of little ring down at the end. During that time, the black holes are moving together, closer and closer, and they're going faster and faster. At the end, they're going more than half the speed of light, orbiting each other. So how do we read that out of this? First of all, this is the time trace that we see from Hanford. And you can start to see, when you look at this, that here's the evidence of the early part of that waveform as they're spiraling together. Here's where they're touching, and then it's kind of ringing down a little bit. You can see a little bit of hint of that. The waveform at Livingston, shown here in blue, has a similar kind of character. What we've done, however, is take this waveform, the one from Hanford. I've flipped it because the orientation of the 2 detectors is such that the signals come out the negative of each other. And I've shifted the Hanford one by 7.1 milliseconds because the gravitational wave arrived at Livingston 7.1 milliseconds before Hanford. Now the 2 detectors, if the gravitational wave were coming in exactly along the line connecting them, it would take 10 milliseconds to travel from one to the other. When it's coming in at an angle, they're a little bit closer together. So we know a little bit about where the gravitational wave source was for this one. And when we line those up in the best possible way, you can see that we get very, very good agreement for the shape of the wave. There's a little bit of disagreement, but it's always within the noise level of the measurement. And in fact, it's that very, very good agreement that we get from the 2 detectors occurring at essentially exactly the same time that gives us confidence that this is a real signal. Now we have from general relativity the best fit waveform that's predicted from numerical simulations of Einstein's theory of general relativity about what these 2 black holes would look like. And that waveform is here, filtered in the same way that the data are here. So when we see that, and we've got this exact same waveform here, just shifted by that same 7.1 milliseconds. When we subtract those best fit waveforms from the actual data, we get down here to the place where we see just ordinary old noise, nothing, no residual signal. And that tells us that this signal matches very well the predictions of general relativity. We also look sometimes at the spectrogram, which is just a measure of the energy at a particular frequency as a function of time. And an in-spiral signal like this has a very characteristic chirp. It starts at low frequencies and then goes to high frequencies and then just ends. So from that, by that comparison, and by looking for exactly the frequency at which the signal ends, exactly how it comes up to the middle, we get the source parameters that we can, for this event. We can determine what are the masses of those black holes, how far away were they. So the two black holes, one was 36 times the mass of our sun, the other one was 29 times the mass of our sun. There's small errors on those numbers, but really very, very accurately determined. Now those two objects were not things that we had expected to see with LIGO. People hadn't ever seen a stellar mass black hole larger than about 20 solar masses. And so nobody had really said, gee, we're going to see a whole bunch of 30 solar mass black holes out there. The final mass of the black hole that was formed at the end was 62 solar masses. And you might say, well, wait a minute. Those two guys added up should have given a full 65 solar masses. The answer is that 3 solar masses of energy, 3 solar masses were converted into gravitational waves and radiated in that last final burst. Now remember, that wave took approximately 2/10 of a second here, okay? So during that 2/10 of a second, this system radiated away 3 solar masses of energy. For that 2/10 of a second, this system radiated more energy than all of the stars in all of the galaxies in the entire universe. Okay? This was by far the most, in fact, it's 50 times the amount of light radiated by all the stars in all the galaxies in the universe. It's an extraordinarily energetic event. Okay? And we could determine the distance, 400 megaparsecs. A megaparsec is about 3 solar masses, or 3 light years. So this is about 1.3 billion light years away. Okay, but we'd like to do more. I mentioned that we could tell a little bit about the location of the source of this by looking at the timing of when did the gravitational wave hit first our Livingston detector and then our Hanford one. So if the two detectors are here and here and the wave is coming in like this, it'll hit first this one and then hit this one. It comes in as a plane wave. If it's coming in like this, it hits the two of them at the same time. But that gives us limited information because it could be coming in like this, but it could also be coming in at this angle. So we can only determine from our two detectors that it comes from a big circle on the sky in kind of the southern hemisphere. Okay? What we'd like to know is exactly where did this come from, because we'd like to be able to tell astronomers, go and look and see, did you see anything interesting in that part of the sky associated with this event? With just the two detectors, we aren't able to really give those astronomers a good location to look for. So what would we like to do? We'd like to have another detector. Unfortunately, we have some friends in Europe. There's a collaborating project called the Virgo project. They're building a detector near Pisa, Italy. It's a 3-kilometer long detector, just a little bit shorter than the LIGO ones, but it has comparable sensitivity. They built a first-generation detector just like we did. They looked for gravitational waves just like we did. They didn't find any with their first-generation detector. And just like us, they're in the process of building this second-generation detector called Advanced Virgo. And now with these 3 detectors, we'll be able to triangulate the position of the source by looking at the arrival time at all 3 of those detectors. And when we do that, well, okay, here's a picture of Virgo. You can see they've got similar configuration. It's a real thing. With the 3 detectors, we'll be able to triangulate and locate the location of sources on the sky. This is a picture of the sky, a map of the sky, and these ellipses that you see here show the accuracy with which we can identify the location of a source coming from that part of the sky. Now, it turns out that when we're trying to locate sources, we get our best resolution for waves that are coming down perpendicular to the triangle formed by the 3 detectors. So with these 3 detectors, we can locate sources fairly well up in this part of the sky. That's the northern point that's perpendicular to the plane of those 3 detectors. This is the southern region, because we can see waves that come through the Earth, they come through completely unattenuated. But this marks the plane of the detector where we don't do so well. So for waves that are coming in parallel to the plane formed by those 3 detectors, we get only these very elongated ellipses for the localization. So the way to deal with that, of course, is more detectors. And what we would like to do is we have another project that's collaborating, that's building a detector in Japan. It'll come online possibly with first light in 2018, maybe sensitive operation by 2020 or 2021, a little unclear. But we'd like another one, and in fact, there's this project called LIGO-India, which is a collaboration between the LIGO laboratory in the US and 3 institutes here in India, RRCAT in Indore, the Rajaraman Center for Advanced Technology, the Institute for Plasma Research in Ahmedabad, and the Inter-University Center for Astronomy and Astrophysics, IUCA, in Pune. Those 3 institutions had proposed to the Indian government a collaborative project where LIGO would provide the detector, just like the ones we used in the LIGO US facilities. If India will build the facility and provide the people to learn how to install it, operate it, and participate as full collaborators in this mission. And with LIGO-India, we would be able to do the following. With LIGO-Virgo plus LIGO-India, we would be able to locate sources essentially over the entire sky with accuracies such that we can tell astronomers, quick, go out and look over there. That's where something was happening. Just to remind you, that's how bad things are without LIGO-India, and that's how good they become once we have LIGO-India. When we showed these 2 figures back and forth to our funding officers at the National Science Foundation, that's what sold the National Science Foundation to support this collaborative project called LIGO-India. And indeed, the 2 countries have now signed an agreement. This is the Secretary of the Department of Atomic Energy here in India, along with the Director of the National Science Foundation, which funds the LIGO activities in the US, and they have just signed an MOU to create this LIGO-India project and move forward. So we're really excited about this. It's going to mean a lot of good collaboration between LIGO in the US and our colleagues here in India, and I think it's going to be a great opportunity for Indian technology and for Indian science. So I'm just going to offer a final thought. I've been involved in this project since 1980, and I think personally that this last few months, as we've convinced ourselves that we really made this detection, I think it's about the most exciting thing for gravitation and relativity since it was really first formulated in 1915. And I think the excitement that came about after this event was the world expressing that same kind of feeling, that it was an exciting time. It was a particularly exciting time for me as well. But I have to say, the best is yet to come. I think we have lots of interesting things to see in the future, other types of gravitational wave sources, and I think we're really on the verge of a great era of gravitational waves. Thank you very much. And I'm happy to take questions if...
Hello, any questions?
The discovery of gravitational waves in the 100th year of prediction, is it a sheer coincidence or there was some kind of plan for that?
It turns out it was a coincidence. There were several of us who were really rooting for 2016 because 2016 is the 100th anniversary of the prediction of gravitational waves. 2015 was the anniversary year for general relativity. So it could have happened either one of those and been a very happy event. There was another interesting coincidence, which is this event occurred on September 14th, 2015. I mentioned that I started work in this in 1980. My official formal retirement date was September 15th, 2015, the day after this was discovered. And I assure everyone that one is a coincidence.
Like if there is a so how the detector will detect how it will interfere, the gravitational waves will interfere from the different events, or like if more than one events are happening in the universe like at the same time?
Yeah, first of all, the gravitational waves, we don't expect the significant numbers of collisions between these. We saw one event in 16 days worth of data or 20 days worth of data that we analyzed in the beginning. So we expect that rate will go up as we get more sensitive, but I don't think it's going to ever be such that we're going to see several events piled up on top of each other. But with multiple detectors, we would even be able to disentangle those because the wave would be slightly different times at the different detectors. So even if they were piled up, I think there's a fair chance that we'd be able to disentangle them.
Thank you.
Thank
you. I have a slightly historical question. Why have these two particular sites in Hanford and in Livingston been chosen?
There are a couple of reasons. We went through an elaborate site selection process, and we wanted two sites that were far apart in the US, but they also needed to be relatively remote, very flat, because that helps minimize the cost of construction, because the laser beams have to travel in exactly straight lines, and you want them to be traveling as close to horizontal on the Earth as you can make them. So we needed to find two very large places that were relatively remote and very flat in the US, and these were in a sense, the two farthest apart ones that met that criteria. So that was the reason. There's some other operational reasons why we preferred these to some of the other nearby sites. For example, the site in Louisiana, we had very enthusiastic support from a nearby university that wanted to build up their group in gravitational wave astronomy. And so they offered to hire faculty who would work at the site and bring students and so on. And so we took advantage of that as, again, another part of the factor of site selection.
Any other questions?
So you mentioned about the Louisiana State University's involvement. So from the LIGO lab and the project, how was this big community of gravitational wave physicists developed in the US?
Yeah, the original proposal was, for LIGO came exclusively from Caltech and MIT. And they formed the LIGO Lab, which is an organization that is a bit hierarchical. It's a very good organization for building something and operating something. But it doesn't necessarily instill all of the creativity that you'd like to have in a scientific collaboration. And our director in the early 90s, Barry Barish, recognized that the best way to get the most science out of LIGO was to keep the construction housed within the LIGO laboratory and the operation, but to try to build an autonomous, a semi-autonomous collaboration of scientists who would be self-governing and would do the science, the data analysis, the future R&D, and engage the other outside communities. And so he particularly identified a few places where universities had expressed some interest, like LSU, Stanford, Milwaukee, several universities like that, and convened a set of meetings, a couple of meetings, where he encouraged them to form this thing called the LIGO Scientific Collaboration. It became then a self-governing thing. We elect our own spokesperson. All of the scientists in the LIGO lab are members of the LSC at the same time that they're members of the LIGO lab. So when I'm doing LIGO lab kind of work, I do it because my boss tells me, go do that thing. But when I'm thinking about science, I do that typically as a member of the LSC. So when I'm thinking about what should a next generation detector look like, I'm not thinking about that because my boss told me to. I'm thinking about that because I'm a scientist and curious and so on. And then I have to sell that idea to my scientific colleagues in the LIGO Scientific Collaboration. So it's those two entities, it's oftentimes a little hard to describe exactly how they operate. LIGO operates the detectors, but as soon as the data are on disk, the ownership of the data transfers really to the LIGO Scientific Collaboration. So when we created this collaboration between LIGO and Virgo, it was not a collaboration between the LIGO laboratory and Virgo. It was a collaboration between the LSC, the LIGO Scientific Collaboration, and Virgo, because the LIGO Scientific Collaboration is the organization that kind of owns, as you will, the rights to the data. And it was the LIGO Scientific Collaboration that had to buy off on the agreement to collaborate with Virgo, not the LIGO laboratory. So it's a funny kind of arrangement, but it's one that has worked very effectively, and it's hard to describe, but we just kind of know how it works, and it seems to work pretty well.
Yeah, Rajesh?
Hello. I don't know whether I'm fooling myself visually, but in the signal of the Hanford and the Livingston, was it that the Hanford one was slightly stronger? I mean, when you superposed, was it, or it's just a sort of statistical?
It does look slightly stronger. I think that's just, I don't think that that's a statistically significant thing, or maybe it's just, there are slight differences in the antenna patterns for the two detectors because they're at different points on the Earth. So if they were side by side, they would have exactly the same signals. But when you move them like this, the response of the detectors to a signal looks kind of like a giant peanut. It's strongest perpendicular to the L, and weakest in the plane of the L, but only by about a factor of 2. They're almost omnidirectional. So it's possible that this source was in a place that just gives a slightly stronger signal at Hanford than in Livingston. And maybe we really are seeing a little bit of that in this.
Yeah, I wanted to follow up on your response to Ajit's question. So it was very interesting the way you described the structure. I was wondering, did there have to be a sense of letting go by the central entity, and were there growing pains associated with that, or did that come just naturally and organically?
Of course there was a sense of letting go. I didn't want to let my data be taken over by this other organization. What kind of a person do you think I am? Generous or? So no, yeah, there certainly was. But I think there was also, it came. Those of us who had been working for years on this project, I think many of us had somewhat parochial views, and I will claim to have held some myself. And it was only after this collaboration really got working, and you start to see the benefit of having this larger community with inputs from them. Sometimes those inputs are crazy, and sometimes they're brilliant. But that give and take of science is really quite good. I mean, there were growing pains when we formed the collaboration between LIGO and Virgo for the same reason. The LIGO scientific collaboration, our detector was more advanced than Virgo at the time we formed that collaboration. And so when we agreed to completely share the data, everything would be published. So even though this event was detected only by the LIGO detectors and Virgo was not operating, all of the Virgo collaboration members co-authored that paper with us. It was there was a lot of controversy within the LIGO scientific collaboration about whether that made sense. But I think now, if you ask the people in the LIGO scientific collaboration, did we do the right thing? I think the answer will be overwhelmingly, yes, we did the right thing. And I don't think anybody feels that their contributions have been demeaned because they're on a 1,000 author paper as opposed to a 750 author paper. But human nature is we're all human.
Sir, what is the plan for future increase of sensitivity of Michelson interferometer?
Yes. So the question is, what are the plans for the future sensitivity? We have not yet even achieved our design sensitivity for this detector. We're currently operating with less laser power than we have the potential to have. I showed you that laser and said it's a 200-watt, highly stabilized laser. Well, the first thing that people do when we're just starting out operating this, which we are just doing that. This was our first observational run. We turned the laser power down to 25 watts so that we would be able to more safely get experience with the detector. So over the next couple of years, we'll turn the laser power up from 25 watts to 200 watts. That will let us gain sensitivity in the region where we're limited by the shot noise, the counting statistics of the photons in the light. So we'll be able to gain about a factor of 3 in sensitivity at high frequencies. We have some work to do on that suspension system. There are ways that we can improve its isolation by changing the way the control loops that do the orientation for our mirrors and control their positions. By tuning those more carefully, we'll be able to get another factor of 3 probably in sensitivity with this detector. Then there are ideas of additional things that we can add on. There's something called squeezed light, which is a different state of light manipulated from ordinary light that would let us get a little bit more sensitivity. People are talking about ways of having better mirrors or different types of mirrors, possibly cryogenic mirrors at cold temperatures. So all of those ideas are being kicked around, but we have in the very near term a factor of 3 that we think we can gain.
Thank you.
What are the odds that this is not due to some terrestrial noise? And what are the precautions taken to ensure?
Right. That's one of the things that we were very careful and very concerned about from the beginning is, could this possibly be caused by something that was terrestrial? The first thing is we continually monitor all of the potential disturbances at our observatories. So our observatories are surrounded by seismometers, accelerometers, microphones, electromagnetic antennas, magnetometers, anything that we could think of that might possibly disturb our instrument. We've got a sensor for that that's designed to detect that. And when we see this event, we quickly rush out and check all of those sensors, all of the seismometers, all of the magnetometers, the microphones, so that we see that there was no disturbance from the external environment that could have caused this. Then the question is there something possibly internal to the instrument that might have caused this? For example, in that suspension system, we've got some wires that are under great stress. And there's possibly a mechanism where there might be a stress release in that wire. And that would cause the mirror to move. Those things happen. That's, stress release happens in any kind of structure that's under stress. Airplane wings, for example, are a great place to have stress release. But the fact that we see exactly the same signal at the same time, we know that we don't see events like this very often. And in fact, we can actually, by looking at the full data set, we looked at 20 days worth of data and said, how many times do we see an event that looks like this at Hanford, and how many times in that entire 20 days, not at the same time, do we see an event that looks like this at Livingston, and what's the chance of that happening at the same time? I'll tell you that this is the loudest event during that entire 20 days in Hanford, and this is the loudest event during that entire 20 days in Livingston, and they occurred at exactly the same time. And the chance of that happening by just coincidence is so small that we are convinced that this is a real gravitational wave. So there's a lot more details that I could explain to you about that, and some qualifications about what do I mean loudest event, but that's the basic background.
Stan, some people are exploring replacing photons by electrons. Would you have a comment on that, to make the arm of the interferometer much smaller?
I know I'm more familiar with techniques to use atoms, actually atom interferometry. Atoms have very, very short wavelength, de Broglie wavelength. And so there are ideas about how to use atom interferometers for this kind of operation. The difficulty with atom interferometers is that whereas it's easy for us to get 200 watts of photons, that's a huge number of photons, and so we actually win by the square root of the number of photons. It's much, much harder to get a large number of atoms into the same state and operating coherently. And so the challenge is to get enough atoms into sort of a coherent state to be able to get the same kind of resolution that we get. There are people working on it, and I think they're about in the same state that we were in kind of in the mid-70s in terms of where optical interferometry was. So I predict those guys may well surpass us in sensitivity 30 years from now.
Yeah, there's a last question there.
So,
what is the implication of this discovery on the theories of on the formation of the universe? Big Bang theory is the accepted theory, no? So, do this discovery in some way affect the Big Bang theory in the sense, do we need to suggest some changes to the theory or something like that?
So he's asking about the implication of this discovery on cosmology, whether Big Bang has to be replaced.
I don't think there's any hint that because of this discovery that the Big Bang needs to be replaced. However, once we actually start to see more of these events, and if we improve our detector the way you suggested by that factor of 3, we would start to see, when we improve the detector a factor of 3, we'll see 3 times farther into the universe. That means a volume 27 times larger because these detectors are largely isotropic, they're omnidirectional. So when we get that additional sensitivity, we might be seeing an event like this every day or two in the future. Once we get that kind of data rate where we're seeing lots of these events, then we can start to try to look at some of the cosmology implications. Do we map the same kind of cosmological expansion using these things as people do with other techniques? So we'll start to be able to do some kinds of tests, maybe not high precision tests yet. Those I think will require a significantly more capable instrument.
I think with this, my daughter had a question. She was wondering where's the energy coming from, the 3 solar masses? Why is it 65 minus 62 equals 3? And we were actually discussing with Ajit and Co on the table yesterday, and we weren't sure, are the rest masses allowed to deplete? So where is the energy coming from?
The energy was radiated into the gravitational waves, and it came from the masses of the black holes. In other words, the 2 black holes, before they merged, were 65 solar masses, 36 in one, 29 in the other, and after they merged, they were only 62. So the gravitational, the black holes actually lost mass in the gravitational waves. So that's where it came from.
So the mass left the horizon.
The mass left the horizon, yeah. Exactly, I don't know.
Is there a theory on that, like M1 and merges with M2 and we know exactly how much energy comes out?
People have solved Einstein's equations numerically, and this is consistent with those numerical solutions. I'm not sure I have a mental picture about how the energy gets out of the black hole, how the mass gets out of the black hole. Bala is probably the more expert of this.
No, I think we should not think that it's coming out of the horizon, because it is essentially these 2 bodies going around each other, and therefore it doesn't have to come out of the horizon. It's essentially the energy which is outside, which is converted to gravitational wave energy. So there's no question of having to escape the horizon of the black hole or anything like that. Even the last part which he showed, the black hole forms and the black hole rings. So the issue of coming out of the horizon doesn't arise in this particular case.
Then the rest masses contain the angular momentum and the kinetic energy also to start with?
So essentially it is, the fact is you have a total energy of this particular system, right? And this orbital energy which you have outside is what you're sort of eventually losing And then that's getting converted to the mechanical energy, energy in the gravitational waves. So the mechanical energy and angular momentum of this particular system, and you define it correctly, within relativity, that is what is correctly balanced. The loss in that is correctly balanced by the emission of gravitational waves. That's what the theory basically shows. I think with this question, I think let's end the session and thank Stan for taking us on this wonderful voyage. Thanks.
Thank you very much. Thank you, Bala.